Hello everyone. This is week 6 of the NPTEL problem solving session for the course Introduction to Algorithms and Analysis. In this week, the primary topics that were covered were randomly built binary search trees, their analysis, the expected height, uh, and the expected depth, and what is the complexity of accessing a node, any particular node. And then there was discussion on a particular type of binary search tree called red-black trees. Then discussion was on augmentation of data structures. And then interval trees. So what we are going to do is we are going to take some problems on some of these topics that are helpful for this week's assignment. And while discussing those problems, I will also try to give you a theoretical justification of what we are doing, why we are doing, and so on. So I think let's start straight away with the problem, right? So given n d digit numbers, in which each digit can take up to k possible values, radix sort correctly sorts these numbers in basically what order of time complexity. So it is theta of d plus nk or theta of d times n plus k or theta of d plus n plus k or theta of dnk. Right, so to do this, let us recall what radix sort is and how does it work. So for radix sort, what we do is we take our array, let's say A, that has some numbers in it, right? And then we divide each number, like we divide all the numbers into digits, right? So these are n numbers divided into d digits. So each block here is a digit, right? And what we do in radix sort is basically we take one digit, right? Take array of one digit at the least significant position, right? So we start with the least significant portion of the resulting number, right? And then we sort that array using counting sort, right? So do that for each array, right? This is basically a radix sort. So to get the time complexity, we need to check the time complexity for first counting sort, right? What is the time complexity of counting sort? So we are given that we have n numbers, and every number can have at most at most k possible values, right? So the time complexity for counting sort, right, for n numbers that can take k possible values is basically theta of n plus k, right? Because we need one pass each of the main array, the resulting sorted array, and the counter array, right? And these are the orders of the original array and the counter arrays. Now, since this algorithm is run for each array, and how many arrays we have? We have d arrays because we have broken these numbers into d digits, right? So the final complexity for radix sort is basically d times the complexity of counting sort, and in the theta notation it can be written as d times n plus k, right? So correct answer is option B. So for this we just had to know first of all how radix sort works and the complexity of counting sort, or essentially how counting sort works as well. That is a part of how radix sort works. Let's take another example. Uh, a red black tree with n internal nodes has height what? Right, so it is less than equal to 2 log n plus 1 greater than equal to 2 to the power log of n plus 1. It is less than equal to 2 log n, or is it just less than 2 to the power of log n? Okay, so basically we want to get the either the upper bound or the lower bound on the height of a red black tree, right? That has n nodes, right? So we start by how it was introduced in the lectures, that we start with the intuition that we merge red nodes into their black parents, right? So basically that gives us some idea of of the height of the red black tree. How does it give us an idea? So if we have, let's say, a red black tree like this, say, this is our red black tree, and it follows all the properties of the red black tree as of now, that all the leaves or the nil nodes are black, and the root node is black, right? All these nil nodes are black. The root node is black, and every red node has a black parent node. Sorry. So it follows basically what the properties of red black tree. So once we have this intuition, right? So this original red black tree, right? It turns into, right? So turns into this tree of different number of leaves, right? So it has either two or three or four children, right? It can only have a maximum of those kind of numbers, right? So let's say this is tree A, this is tree B. So in B, each node has two, three, or four children, right? Not less than that, not more than that, right? And also the two, three, or four children tree has a uniform depth, like on average, h star of leaves, right? And it also implies that h prime, sorry, h prime, not h star, will be greater than equal to h by 2, right? Why? Since at most half the leaves on any path are red, right? So in any path, since at most half the leaves are red, so therefore the height of the subtree that has been made by considering only the black nodes will have a height larger or equal to h by 2 because it has more nodes than h by 2. So, so what does this give? This gives that number of leaves in each tree is n plus 1, right? Because again, like on an average, number of leaves in each tree is n plus 1. So we can relate this number of leaves as the number of leaves should be greater than or equal to 2 times the h prime. No, 2 to the power of h prime, right? Because the total number of leaves for any binary search tree is greater than or equal to 2 to the power the height, right? 2 to the power of the height of the subtree. So if we take log base 2 at both, sign does not change because this is a monotonic function. This is h prime, and we know that h prime is greater than or equal to h over 2. It means that the height of the original subtree is less than or equal to 2 times log of n plus 1. So less than or equal to. So we have an upper limit on the depth of the red black tree. So let's take another example. Jensen's inequality states that for any concave function f, and a random variable x, uh, basically we need to identify Jensen's inequality out of this for a convex function. Either this, or is the value of the expectation less than the, not equal, just less than the expectation of the value, or is it that the value of the expectation is greater than or equal to expectation of the value, or none, right? So which one of these is the Jensen's inequality, right, for a random variable x and a function f? So what we can do is we can prove this again by just using the pr- proof that, or by using the statement that f is a convex function, right? So it can be written as the f of, like, the expectation we can write as from minus infinity to infinity x times probability of x equal to k, right? This is like the definition of the expectation operator, right? And since f is convex, it means that f of summation of x, right? So f of summation of xi or let's say alpha I xi is less than equal to the summation of alpha I fi, right? For all I. So similarly here also alpha I xi is less than equal to the summation of f of k times for all k, right? And now this is the definition of expectation of a function of x, right? And this we saw above that this is the f of e of x. This is less than equal to the expectation of f of x. And what we did here was we made a mistake that we assumed that f is convex because f is given to be concave. So since f is concave, so all these signs they revert, right? So the value is always greater than, like, the function's value is always greater than the value that it is evaluated at. And so this will be the relation for concave functions, right? Jensen's inequality for concave functions. So the answer is C. Let's take another problem, right? Given the numbers 1, 3, and 2, how many randomized binary search trees can be formed. Okay. So let's not write the options for this because we can just work our uh, way here. That we have three numbers, 1, 3, 2, and we need to arrange them in a binary search tree form, right? So all these numbers can be arranged in max 3 factorial ways, right? So that gives us the value 6. But 2, 1, 3 and 2, 3, 1 are same, right? Because this is essentially these two binary trees are the same, right? So in total, there are 5 randomized binary search trees that can be found. Let's take another example. A red black tree on n keys realizes the largest possible ratio of red internal nodes to black internal nodes when option A each black node has 2 children, option B each red node has 2 black children, each black node has 2 black children, each red node has two red children, right? So, like, we want to make a valid red-black tree that has the largest possible ratio of red internal nodes to black internal nodes, right? So, first of all, C and D, right? They are not like uh, even valid red-black trees, because for red-black trees, the red nodes should have a black parent, right? And both the options violate that, right? And also for B, again, red nodes should have black parents, right? But it does not say anything about the children, right? And also, if we want to have the maximum ratio of red as compared to the black, then of course we need to make sure that the black nodes have two red children, right? So that the total number of red internally is more, right? So it should be like this, right? So these are the internal nodes, right? So of course in this case, since every black node has two red children, the ratio of red to black is high, right? So here the answer is A. Another example, what is the time complexity of finding a node in a red black tree? Right, so is it linear or is it logarithmic? Is it n log n or is it constant? Right, so let's consider this red black tree, right? So to find any node, we just at every step we need to go one level down, right? So in the end, we need to traverse the height of the tree, right? And the order of finding a node is the same as the order of height of the tree, right? Because essentially it's a walk down the tree, finding the node, right? And what is the order of the height of the tree? That is log n, right? So the order of finding a node is also log n, the same order as the height of the tree. Yeah, let's continue. So another example is in a randomized binary search tree. The expected number of leaves is n squared plus 1 over 3 n plus 1 over 2 n minus 3 over 2, right? So we want the average or the expected number of leaves when we are doing when we are making a randomized binary search tree. Okay, so we can try to approach this as that after we have inserted n nodes, let's say we have f of n leaves, right? And of course we have f of 1 as 1 because for one node there is only one leaf, that is the node itself. Right? And then out of n plus 1 places that new node could be inserted. So 2 times f of n of those are underleaves. Right? So basically we have our f of n. It's out of n plus 1 total places, 2 times f of n places have been used, and that now gives us the new number, right? The remaining number of leaves, right? So when it all converges, it will become 3f of n equal to n plus 1. So f of n is basically n plus 1 by 3, right? So this is a simplified solution of this problem, that what is the average number of leaves for a randomized binary search tree, right? So I think the all these problems will are enough to help you while doing the weekly assignment. And if you have any questions, then of course you can ask on the forum. So I think I'll stop the meeting now. Thank you.